Welcome everyone. So last class we completed our discussions on variational divergence minimization, which is the adversarial learning part. Now we will move on to the next class of models from this class onwards, which are the latent variable models. As I said, this is a broad paradigm within which a large family of models come in. For instance, autoencoders, variational autoencoders and all its variants. Even some classical machine learning models such as mixture models and mixture densities fall in this category. So, we will look at what the formulation of latent variable models is, and then we will look at a few examples of latent variable models which constitutes generative models. Specifically, variational autoencoders and its families is something that we will see immediately. Before that, I'll give you a brief overview of the classical mixture density as well, so that it can nicely lead on to the need for neural models. Then we will get to these family of models called diffusion models or DDPMs, denoising diffusion probabilistic models as they are called. Then we will look at score based models and flow based models. All of these can be categorized within the family of latent variable models. So, what is the idea? We are given n data points that are sampled IID from an unknown distribution, that is what we start with. Our goal remains the same, we need to estimate the underlying distribution and try to sample from it. So, let us say p theta denotes a parametric model. Okay. Now, latent variable model is a mathematical definition of how you look at p theta. The definition goes as follows: if you define a model as the marginal between the observed data variable and another auxiliary variable that the model incorporates, and you model or you define the model distribution p theta of x as the marginal over the joint distribution between x, which is the observed data, and z, which is called the hidden representation or hidden variable or latent variable. That is why the name latent variable models. Okay. So, this z is not observed, this is not given. Most of the cases this z is going to be jointly learned with theta. When we learn the model parameters, we also learn the latent variables. Okay. This is if the latent these latent variables can be continuous or these can be discrete. If it is discrete, then the marginalization involves a sum. If it is continuous, then it is an integral. So, definition of a latent variable model is that p theta of x is taken to be a marginal over the joint distribution between the observed data x and a hidden variable theta. So, that is the definition of a latent variable model. Now, the z is often referred to as the latent variable or hidden variable, unobserved variable. Yeah. So, as I said, typically z is jointly estimated along with the model parameters theta. That is what you do in a model. Okay. So, now conceptually here is what is happening for each xi, which is a realization from the random realization from the distribution that we are trying to estimate. We assume that there exists a zi corresponding to each of the xi that we have in data. So, now for a given data realization, there is a hidden realization is what we say in any latent variable model. Okay. So, now let me give you examples of what these latent variables may represent. Suppose z is discrete, latent variable is discrete. Let us take that example. Suppose the latent variable is discrete. So, in that case z can take 1 out of m possible values. So, this is what the random variable being discrete mean, right. So, you have this latent variable taking 1 out of m values. Note that I am not putting any conditions on what my data variable is, right. X can still be RD. So, let us say that my x is still in RD, it is some image or something. Okay. Now, I said in a latent variable model we associate one z corresponding to each of x, correct. So, for each xi in D, so there exists a zi. Okay. Now, in the case of a discrete random variable, suppose we construct a latent variable model and get one particular discrete value of z for each xi, what do you get after you do this exercise? You are essentially grouping all the data that you have, okay, into m groups if you have discrete latent variable. Do you see why? Because every xi will be associated with one zi, and this zi can take one out of m possible values, which means that all the xi's that you have in your data set are now grouped into one out of m categories. And that is why realizing a latent variable model with a discrete latent variable is also known as clustering. So, all the clustering algorithms that we see are latent variable models with the latent variable being discrete. So, because what do we have is, we get zi for every xi, and now this zi can take one out of m values. Once we do this post inference, what are we essentially doing is grouping all this data sets into data points into one out of m categories. Make sense? Okay. Now, if z is continuous, in that case what we have is zi can be a k dimensional random variable. So, now for every xi we have one k dimensional vector associated with it. What does this correspond to? I mean, see, this is the I will just give you one or two possible explanations of what this may correspond to, but this may not have any physical consequence whatsoever. However, let us say that we are looking at mness data set, okay. We have some digits. Now, this z, let us say z has 4 dimensions in it and there are 4 numbers. This z may correspond to, one of the dimensions of z may correspond to, let us say, the thickness of the digit, the other dimension may correspond to the orientation of the digit, right, the other may correspond to something else. So, now I am not saying that once you construct a latent variable model it always have some physical association with it. I am just saying this, there may be a correspondence. So, now coming up with latent variable models with interpretable latent dimensions is an open problem. I mean, you can actually come up with interpretable latent variable models, but in the case of a continuous latent variable model, each dimension of this latent variable may correspond to some feature of the data, okay, which may or may not be interpretable. But when it is discrete, you can always see that as clustering. Does it make sense? Okay. So, I said if zi is discrete, then each xi is clustered into one out of m categories. That is why all the clustering algorithms can be seen as latent variable models with discrete latent variable, including your Gaussian mixture models and k-means clustering, hierarchical clustering, and all these are latent variable models that way. If z is continuous, then zi given xi represent a feature vector corresponding to a given zi. By the way, this is what is called as embedding. So, whenever you are extracting some embedding for data, essentially what you are doing is constructing a latent variable model and estimating zi given xi, or sampling from the distribution of p of zi given xi. We will see that later in this class, but yeah. So, zi given xi is what is called as embedding. Okay. So, there are standard models with which you can actually get embeddings for images and text and so on. So, last class, remember when we talked about FID as a metric to evaluate a generative model, the vectors that we get from a pre-trained model, right, can be seen as embeddings. That model can be seen as a latent variable model, okay, that way. Okay. So, latent variable models can also be used as generative models is something that we will see now, and see, the advantage with the latent variable models is that it will give you both ways, meaning that by construction you can obtain the embeddings corresponding to each of the data point, which is zi given xi, you can also sample data from these models. So, it will serve both the purposes. So, it will have an encoder that will take X and project it onto the Z space, which is the embedding extraction part. It has a decoder that will take Z and gives you points on the data space, which is sampling. So, both of these things happen. Okay. So, what is the general principle for learning latent variable models? It is the standard process of a maximum likelihood estimation. Okay. Typically in latent variable models, the divergence metric that is used is KL. So, there are constructions where latent variable models are built using some other divergence metrics as well, but mostly it is the KL divergence that is used. Now, suppose I will just walk you through that. Suppose we are given n data points that are sampled ID from an unknown distribution. P theta is now given as the joint distribution between marginal of the joint distribution between these two, right. The goal is to estimate the model parameters theta given d, and the metric that we are using is the KL divergence. Okay. Now, write the KL divergence as expand the KL divergence using its definition, and the integral px log px by p theta dx can be split into two integrals, integral px log px minus integral px log p theta dx. The first term is independent of theta. What is this, by the way? This is the entropy of data. Entropy of data has nothing to do with models, right. I mean, data is there, you can't do anything about the entropy of data. So, that by tweaking theta, I mean, no matter what you do with your model, the entropy of the data does not change, right. So, it is like you can't change the universe no matter what you do. So, it is quite philosophical that way, right. So, all you can do is tweak yourself. So, self tweaking is theta, you can change yourself, that is under our control, you can't control anything outside of you. So, that is entropy of universe or the other person, just leave it that way. So, it is independent of theta, that does not even figure in your optimization problem. The second term is what survives, and that is the negative of integral px log p theta x, which is the expectation of log p theta x with respect to px. And since there is a minus sign here and we are minimizing the KL divergence, if you push it outside, it will become maximization problem, and this is the standard maximum likelihood estimation problem. So, from now on, when I write a latent variable model, the objective is now to maximize the expected log likelihood of the model under the data distribution. See, I just expressed this in words, let me repeat what I just said. Our objective is to maximize the expected log likelihood of the model distribution, where the expectation is taken with respect to the data distribution. That is the objective in maximum likelihood estimation, and I keep repeating this, right. Maximum likelihood estimation is minimal KL estimate, they are both exactly the same. So, when we are maximizing the likelihood, we are minimizing the KL divergence, that is what is being done. Okay, this term I will not repeat the definition. Log likelihood of this function p theta of x is the model log likelihood. So, what we maximize is the model log likelihood, p theta is our model, we are maximizing the log likelihood of that model p theta, that is what we are trying to do. Are we good so far? Okay. Now, for a latent variable model, p theta of x would be integral p theta x comma z dz, which is the joint distribution. So, we will just plug it in here. So, let us denote log p theta with L theta for ease of writing. So, L theta is log p theta of x, which is log of integral p theta x comma z dz. Okay. Now I will do a lot of algebra. Before I start that, I will just tell you what is going to happen now. So, note that this marginalization is not well defined, in the sense that we do not know what the joint distribution is, and we do not even know what the latent variable is. We do not even have realization of latent variables, is not it, because all that we have are samples from px, we do not have samples from pz or anything. I also told you that in latent variable models, the goal is to jointly estimate the latent variable along with the model. Now, how do you put it probabilistically? That we are interested in finding out a distribution on the latent variable conditioned on data. This is called the latent posterior. So, what do we need? We need to find out what latent variable corresponds to what data variable, isn't it? Okay. how do you translate that probabilistically? We want to find a distribution on the latent variable conditioned on data variable, that is it. Now, there is no one single latent variable corresponding to a data variable. See, if you recall what you did in GMMs, so GMMs are also called as soft clustering algorithm, right, because given an x, it will give you an entire distribution over that discrete latent variables. Okay. We will see some of it, but anyway, point is probabilistically what we are seeking is, we are not seeking one deterministic value of the latent variable. That happens if your q of z given x becomes degenerate or Dirac delta, in which case for a given x you have one and only one z, which is what will happen in k-means clustering. Okay. However, in general, q of z given x can be an entire distribution over the latent variable given x. So, when I say that we estimate the latent variable jointly along with the model, what I am actually saying is that we are estimating a distribution over the latent variable conditioned on the data variable, which is what I denote by q of z given x. So, this is a very important distribution in the entire latent variable literature, latent variable model literature. This is called the latent posterior. Okay. The one of the primary goals of latent variable models is to estimate this latent posterior given data. Okay. Now, let us say, so okay, so what we will do is that we will somehow bring this into our optimization problem and see if that can be used and involve that as an additional optimization objective over our main optimization. Because remember that we are not only interested in finding out what the model parameters are, but we are also interested in finding out what the latent variables are. So, which means that we have to involve this in our optimization, that is what we are going to do now. Does it make sense? Now, how do we do that? First, you denote some random density function, okay, q of z given x. I should not be saying random density function here, randomness has a particular connotation here, right. So, some arbitrary random density function over the latent variable given data variable. So, q of z given x denote a density function over the latent variable z given x. Okay. Now, our objective is log of integral p theta x and z, multiply and divide this integral by that density function that you are denoting, that you started with. Now, since it is a density function, it is non-negative, all values of it are non-negative, and multiplying and dividing that with an integral does not change the integral, correct. So, that can be done. Now, we do a little bit of algebra, take out q of z given x and group the other terms here. So, q of z given x times p theta of x and z divided by q of z given x dz is what the integral is going to be. Now, we know this, right, we can identify this integral. So, we have this entire thing as a function of z, correct. This item within the bracket can be seen as a function of z. Okay, this is a distribution over z or a density function over z. So, this entire thing now will become an expectation over z, expectation over q of z given x. So, the objective that we have, which is the log likelihood, now can be written as log of expectation of p theta x and z divided by q of z given x over q of z given x. Alright, simple algebra, right, so far so good. Okay. Now, what happens is that, see, we have been what is our go to weapon in this entire course is that whenever we see an expectation, try to express this, estimate that using sample averages and then estimate it. But here we do not have an expectation, we have a log of an expectation, okay, that is difficult to estimate. So, now somehow we have to push the expectation outside of the logarithm. So, can we do that? So, we have seen a lot of inequalities that way, right. One is the famous Jensen's inequality, is specifically when we have a concave function with that. So, we know that the Jensen's inequality tells you that if you have a concave function, then the function times the expectation is bounded by the expectation of the function, is not it. So, depending upon whether the function is concave or convex, this will become an upper bound or a lower bound, that is what the Jensen's inequality tells you. If you do not know what Jensen's inequality is, go back and read and prove that, take it as a homework. just prove that if you have a convex function or a concave function, then the expectation of function of a random variable is bounded. It is the other way around. Yeah, expectation of function is bounded by the function of expectation if f is a concave function, and if it is the convex function, it is the other way around. So just prove that. It is a simple proof to do. So now we will invoke that, because log is it concave or convex? It is a concave function, right. So we can use Jensen's inequality here. So we have log of expectation of this entire thing, which can be written as we can create a Carver bound on this. This is greater than or equal to the expectation of log of this. There is another reason why we do this. Most of the model density functions that we use come from exponential families. So you have this sufficient statistics, you know that, right. All densities from exponential family can be written as product of two functions. That's what sufficient statistics talks about. I mean, Stoma, you would have studied that, which means that if you push the logarithm inside and these densities are coming from the exponential family, then this logarithm and the exponentiation will cancel out there, and the algebra works out to be nicer. That's what happens in a Gaussian mixture model. That is why when people teach mixture densities and the expectation maximization algorithm, which is a way to solve this problem, they will motivate it from this entire thing from a different angle. They will say that, I mean, they will write one particular instantiation of this where p theta of x given z is a mixture density, and show that this entire thing will be intractable because we have log of sums, but we need sum of logs, and that is when then they invoke the Jensen's inequality. But there is a generalized framework behind that, right. The idea is that we want to express the expectation in terms of law of, I mean, the sample averages, and we want to push the logarithm inside. Want to do that, then invoke Jensen's inequality. Okay, everything else, see, this is the general philosophy is, at least the way my mind looks at things is, you look at the abstract ideas and everything that you see will become special cases of it, not the other way around. Because if there are infinite special cases, you can't exhaust all of them, right. If you can find an abstract way of integrating all of it, okay, then you can generalize a lot of ideas. So that's how you look at it. What we are actually coming to is one of the instantiations of this entire thing is what we call as the expectation maximization algorithm. We will see that in a while. Okay, so we carve this this bound on the log likelihood. Let's denote this with j theta of q. Why? It's a function of theta because we have model parameters. It's a function of q as well, because we don't know what q is, right. So what we actually did was we computed or we constructed a lower bound on the log likelihood. The log likelihood is also called as evidence in literature. I mean, it's a nomenclature. So what we constructed is a lower bound on the evidence. So it's evidence lower bound, abbreviated as elbow. It's a lower bound on evidence. So that's why all these algorithms are called elbow optimization. So funnily, there are lots of there's a lot of literature that came around how to re-express the elbow such that the model optimization becomes easier. Okay, there's one paper whose title is literally elbow surgery. So elbow surgery, another way to carve the lower bound on the evidence. Okay, so they say that you can carve it in a different way, and a better modeling performance will emerge there. The paper is titled as elbow surgery, but yeah, so there's a pun there. But anyway, so what we constructed was a lower bound on the evidence function, and that's why it's called elbow, evidence lower bound. So now this j theta of q is a function of both the model parameters theta and the density function on z, which is q of z given x. Okay, see, this q of z given x is referred to as latent posterior. It's also called as variational latent posteriors. I'll tell you why this is called variational latent posterior. See, this whatever lower bound that we have constructed, okay, is an integral that involves q of z given x, isn't it? This is the integral. The expectation is an integral involving q of z given x. Remember last class I told you that there is this entire branch of calculus called variational calculus, which deals with this question of how do you optimize or find an optimal function which inside an integral. How do you solve optimization problems with respect to functions? See, we know how to differentiate with respect to variables, we do not know how to differentiate with respect to functions. So, you need that Euler-Lagrange equations and so on, right. There is a branch of machine learning which is called variational machine learning, where they take the root of variational calculus and the Euler-Lagrange equation kind of roots, where they estimate these latent posterior using those methods. Okay. So, since we are solving optimization over a function which is inside an integral, this function is also called the variational latent posterior. Okay, that's how the name came. That's why the name variational autoencoder also, because we are trying to estimate the function. It's a different thing that ultimately we will approximate all of these using neural networks and convert that problem into a problem of optimization over variables. See, that's what engineers do, right. So, while mathematicians will try to keep the problem that way and try to look at integrals and so on, we convert all of them into a problem that can be implemented using some gradient descent and solve it. Eventually what we will do is we will estimate all of this, we will approximate all of these using neural networks and convert this problem to that of finding the parameters of that neural network. But strictly speaking, you need to optimize over functions. Solving or rather finding the parameters of a neural network using gradient descent is not a functional optimization problem. It is still an optimization over the space of parameters which are variables. Okay. Anyway, so the approximate optimization problem that we would solve, the original maximum likelihood estimation problem was that we need to find the parameters of the model such that the log likelihood is maximized. Now, once we carve the lower bound, the approximate problem is that we need to find the optimal value of the elbow, where the optimization is over both theta and q, where q is the distribution over the latent variable given data. So, this is the problem that we will be solving for GMMs, for any mixed density model, for VAEs, for DDPMs, for flow based models and all of it. So, remember this. Okay, we have two, for any latent variable models, this is the problem that we will be solving. So, there is a lower bound that we have constructed on the evidence. The evidence involves the model parameters and the variational posterior. There is a joint optimization problem that we will solve, one with respect to the model parameters, the other with respect to the variational posterior. Is that all right? Okay. Yeah, that is what I just said. No, the fundamental problem solved in any latent variable generative model is given below: elbow maximization and find theta and q such that it maximizes elbow. So, this boxed item, okay, theta star comma q star is argmax of this expected value of log of p theta x given c divided by q of z given x, and the expectation is with respect to q of z given x, which is the variational posterior. Are we good? So, this is what we do in a latent variable model. So, let us look at what we will do is I will quickly run through an example of this from classical machine learning, assuming that all of you know this already. I do this to set a context to what we do later. So, if we understand this well, then we will appreciate why people had to move away from this and come up with neural models to solve these kinds of problems. Example from classical ML is the Gaussian mixture model, okay, any mixture density for that matter, where z, okay, so mixture densities are latent variable models, okay, where z is a discrete latent variable. It has it will take 1 out of m values. The model that we use here is the following. Okay, before that, the joint density between x and z can be written as in fact in all latent variable models you express that in terms of the product of the marginal over the latent variable times the conditional of the data variable given the latent variable. So, p theta of z times p theta of x given z, and that is simple definition of the conditional density. Okay. Now, in a latent variable model with discrete latent variables, the first term will become a mass function, because z is a discrete random variable. This will become a mass function. The second one will be a conditional distribution with z taking a particular value. Okay. Now, in any mixture density, we take p theta of z given j to be equal to some alpha j. Remember that we jointly estimate this. Anything that has to do with the latent variable is also jointly estimated with the model. That is what we do in latent variables, and that we denote that with alpha. In a Gaussian mixture density, the conditional distribution of the data given the discrete random variable is taken to be a Gaussian density with a particular mean and variance. Okay, conditioned on, I mean, you should think of this mixture density this way. So we have an M phase die, we roll that M phase die, depending upon what phase does it turn out to be, we choose one Gaussian density. We have M Gaussian densities, mixture of M Gaussian densities, roll a die, depending upon what it turns out to be, choose that particular Gaussian density. That's what GMM does. Okay, so we have capital M number of Gaussian distributions, which means we have capital M number of mean vectors and capital M number of variance matrices, and we are dealing in d dimensions, and all these are vectors here. Okay, so that is why the model definition finally p theta will be alpha j times the Gaussian density. Okay, my notation here is as follows, right? I am saying that this is a Gaussian density on the random variable x, parameterized by mu j and sigma j as parameters. Is that all right? Okay, so this is what a Gaussian mixture density is. So it is also called a mixture density because the final model density is a convex combination of multiple Gaussian densities. That is how it looks like. Because why is this happening? It is because the definition of the latent variable model is that it is the marginal over the joint distribution. Joint distribution can be written as product of the marginal over the latent variable times the conditional. Okay, if this becomes discrete, then this entire thing can be seen as a linear combination of multiple conditional densities. That is why it becomes a mixture density that way. Got it? See, if Pz is if z is a continuous random variable, then you cannot see that as a linear combination. Only if it is discrete you can see that that as a linear combination. Are we good? Okay. Now what are the parameters of this model? We have m number of alphas, each corresponding to one throw of the die. I mean, we have it is an M phase die, as I said. We have M mean vectors and M variance matrices. All of these are matrices now because data is in RD. So that is what I have written here, right? Since X is in RD, mu j, which are the mean vectors, are also in RD, sigma are D by D matrices. And our alphas are such that they are between 0 and 1 because they are it's a mass function that we are looking at, right? It's actually probability. So you know this, right? Probability mass function is it's a valid probability measure, not the density function. So it's bounded between 0 and 1, it sums to 1. Okay. Now the goal is to estimate the parameter theta via elbow optimization because it's a latent variable model. That's what we need to do. What is elbow optimization? We need to find the theta star and q star such that this j theta of q is maximized. That's what we need to do. Okay. So now the idea is to solve this optimization problem iteratively, once with respect to theta and once with respect to q. When you optimize with respect to theta, keep q constant. When you optimize with respect to q, keep theta constant. So here one may ask this question: how do we know how to optimize over q? Because it's an optimization problem over functions, right? So just hold on to that. I mean, turns out that if you take a mixture density, this becomes a tractable problem. So now you can actually find what the analytically you can find what the optimal q star is. This becomes important because the question that we will be asking later is, what if we cannot find that optimal q analytically? What do you do in such cases? Is what precisely gives rise to variational autoencoders. Okay. Anyway, so this problem is solved now iteratively between optimizing over q and optimizing over theta. Okay. So we will look at that iterative algorithm which is also called the expectation maximization algorithm, EM algorithm. So let theta t and qt represent the estimates at some iteration t. Okay. So now here is the algorithm for t from 1 to capital T. With theta t as constant, you get the next optimal q. and with q being constant you get the next optimal theta and you keep iterating between those two, okay, which is the expectation maximization algorithm. Now okay, I have actually skipped two proofs here, uh, which is a part of my previous course. I did solve these in my previous course, right? Okay, so go back and refer to that. And for those of you who have not taken my previous course, take this as homework and do it. Two things to be shown. One, you have to show that if I solve this optimization problem the way I am going to tell you now, the likelihood will not decrease, is something that you should show. The EM algorithm will ensure that the likelihood is never decreased. So that is one thing that you should show. This particular way of solving the optimization problem will ensure that the likelihood would never decrease. Note that I am saying that it would never decrease and not it will always increase, because there is an equality here, which means that EM algorithm can actually saturate, and that is a known problem of EM algorithm. So mixture densities are known to get saturated, especially in higher dimensions, because by very construction the likelihood, you can only guarantee that the likelihood would not decrease. So please prove this. This is one thing that is to be shown. The other important thing that is to be shown is that the solution for this optimization problem, which is optimize the elbow with respect to q, has an analytical solution, and that analytical solution happens to be p theta of z given x. Now what am I saying? I am saying the optimal distribution that would maximize the elbow for a given theta is the posterior of z given x under the model distribution, is all that I am saying. Do you see the statement? Do you understand? So remember that we wanted to optimize over q. So when we started all this discussion, we said that q can be any distribution over z. Okay, then we constructed the lower bound. Here I am saying that the lower bound that would optimize this, okay, is the one which corresponds to the posterior of the latent variable given data under the model for that theta. So this is for a theta. So if you fix a theta, then you find p theta of z given x, and that is the distribution that would maximize the elbow. That is what we need, no? So please show this, please prove this. I have proved this in my previous course, but yeah, so do it. I will just tell you how to do it. What is the maximum value that this can take? The elbow, what is the maximum value that the elbow can take? It is a lower bound. What is the maximum value that it can take? And the bound becomes tight, right, which is equal to the likelihood. So the question that I am asking is, what value of q will make this lower bound equal to the likelihood? That is it. So ask that question and try to find out what is that q that would maximize the likelihood, and you will find that to be p theta of z given x. Okay. Now algorithmically what would happen is that I said, remember that our EM algorithm would say that given a theta, start with an arbitrary theta, given a theta, find the optimal q and plug that optimal q back to your elbow and optimize for theta and keep iterating between these two, correct. So how does that happen in practice is that we know that for a theta, q star, which is the optimal variational posterior, is equal to p theta of z given x at that particular theta t, correct. How do you find this p theta of z given x? Use the Bayes law. So that is given by p theta t x given z times p theta of z divided by this normalization constant, correct. Do we know p theta of x given z? We do, because we have assumed that to be a Gaussian, and at theta we are assuming that we know what p theta t is. So we know this. Do we know what p theta of p theta t z is? We know that as well, which is alpha t, which is the value of this the parameters of this distribution at the tth iteration. So we know everything in this expression, and therefore we can compute q star of q star t plus 1. So with that you plug this entire thing into your elbow here, Okay. This will now become a function of theta, and then simply solve this optimization problem. How? Analytically. In the case of GMM, you can actually differentiate this entire thing with respect to mu, alpha and sigma and find what the next estimate is. You can do it analytically, or if you are looking at a mixture density where this problem cannot be solved analytically, you can go to gradient based methods as well. This is how EM is done. Just said, no, the above is solved by differentiating this with respect to theta and solving for theta for a Gaussian mixture density, and you get your mu star to be something of this sort. I mean, you just can do the algebra, okay, just take it up and do the algebra and complete the EM algorithm for a mixture density like GMM. So, yeah, this is assumed to be a prerequisite, so complete this, okay. So, this is the general principle of expectation maximization algorithm, and this EM algorithm is not restrictive to Gaussian mixture densities. So, it can be applied to any class of latent variable models, as long as, what is the only constraint? The only constraint is that you need to be able to find the p theta of zk1x for a given theta. So, any model, any latent variable model in which you can find what p theta of zk1x for any theta, you can apply EM. See, that is why there are these family of models called probabilistic graphical models, PGMs. For a lot of PGMs, the method to estimate the parameters of PGMs is EM, because PGMs are constructed in such a way that p theta of z given x becomes tractable, and then you apply EM to do that. Actually, there are two constraints for applying EM. One, you need to be able to estimate p theta of z given x. The other constraint is that you need to be able to solve this optimization problem, that is, when you plug in the optimal latent posterior, then you need to optimize over theta as well. No, the entire elbow has to be differentiable, or rather, some people take up the usual gradient based routes as well, okay. But yeah, so whole family of PGMs can be solved this way, where you define a model such that the latent posterior is tractable, and the optimization with respect to theta is also tractable in terms of solvability, then you can use the EM algorithm to solve it. However, the question is, suppose you construct a model where p theta of z given x is not tractable. How do you build latent variable models? Okay. So, that is the question. So, how to learn from latent variable models for cases where p theta of z given x is unknown. So, if you read the introduction of the variational autoencoders paper, they start their paper by mentioning that. So, we are interested in coming up with models, latent variable models, for which the variational latent posterior is intractable. That this is what they mean, because EM cannot be applied. EM can be applied only if p theta of z given x can be computed. So, now if p theta of z given x cannot be computed, what do you do is the question, okay. And the title of the VAE paper is not variational autoencoders. Title of that paper is autoencoding variational base, okay. So, I will tell you why that paper is titled that way once we complete the discussions on what VAEs. So, read that paper, autoencoding variational base. So far you can only look at the introduction, because it says that for the cases where the variational posterior is not tractable, how do you build models? That is the question that we will be asking, okay. Any questions so far before we move on? Point is, when you do not have a tractable p theta of z given x, how do you build latent variable models is the question that we will be asking. Setting is the same, that we have data given n data points sampled ID from an unknown distribution, all the data points are in RD, and we are considering the latent variable model, which is defined as the integral or the marginal between the marginal of the joint distribution between the latent and the data variable. Now, we want to minimize the KL divergence, which is equivalent to maximizing the expected log likelihood. That became intractable, and alternate problem, surrogate problem, is that we optimize the lower bound on the log likelihood, which is what we called as elbow, which is which I denoted that as j theta of q, which is an expectation of log of p theta x and z divided by q of z given x with respect to q z given x, okay. Now, if you want to construct a latent variable model, I mean it need not be neural, any latent variable model has to do this. More so a neural latent variable model has to do, I mean I said neural latent variable model because it has to learn a latent variable model with unknown p theta of z given x. So, if you construct a model, okay, it has to be constructed in such a way that it has to learn the latent variable model without explicitly knowing what p theta of z given x is. This is first goal. The second goal is that it should enable sampling or generation from p theta of x given z. So, remember we are looking at generative models. If there is a model that cannot sample from p theta of z given x, it is not a generative model. So, the model by construction has to enable sampling from p theta of z given x. By the way, I did not mention this, any mixed density enables this, any PGM would enable this. Why? Post training, what you can do is you sample a z from p theta of z, which is rolling a die, and then given condition on that z, you sample from p theta star of x given z, which is your data sample. That is why GMMs are samplers, GMMs are generative models. Okay. The third objective is that it should enable what is called as posterior inference, which is embedding extraction, which is that you need to compute or estimate the latent posterior q of z given x. The model has to be capable of giving you q of z given x. Are GMMs capable of doing this? They are. What is this, by the way? Post model training, if you do q of z given x, if you compute q of z given x for a GMM, what is this? This is clustering. So, for every x you get a distribution over z, okay. Z is discrete 1 to m. So, for a given data point, your GMM will tell you what is the likelihood with which this data point is associated with this particular group or cluster. So, posterior inference in a discrete latent variable model is clustering. In a continuous latent variable model, posterior inference is embedding extraction. Get it? Okay. So, any latent variable model has to do these three things. One, learn a latent variable model. I mean this with unknown p theta of z given x is specifically for those models which do not adhere to EM. Then functionality wise it has to enable sampling, okay, and it has to enable posterior inference. We need all three of them to be done, alright. Okay. Okay, so now we have to come up with an algorithm for this neural latent variable model. So we have all this. Now we will break down the elbow a little bit more, where we express the joint distribution between the data and the latent variable p theta of x comma z as the product of p theta of x and z, x given z times p theta of z, okay, and do a bit of algebra. Log of a times b divided by c is log of a minus log of b by c, correct. Just use the invoke the law of logarithms and look at this term. The first term is expected value of log of p theta of x given z with respect to q of z given x. So, that stays. The second term is something that we know how to express. Now, this is KL divergence. So, there is a minus here. Where did this minus come from? Came because I put the denominator up. Okay, why did I put the denominator up? Because I wanted to write it as a KL divergence, that is it, right. I mean I could have put plus here, this one above and wrote it as minus KL, it does not matter, right. So, okay. So, this is the final form. In fact, this is the so called loss function of a VAE and DDPM and so on. So, this is simply elbow being written this way. So, elbow has two terms, one the expected log likelihood of the conditional data distribution with respect to the variational latent posterior minus the KL divergence between the variational posterior and the marginal over the latent variable. When I say it in English, do you understand? And whatever I have written in mathematics, I just use the name of all these distributions and told, okay, that this is what we are trying to optimize. Okay. Now, to do it using neural networks, so we know that that we do not have q of z given x, or rather we have to jointly estimate q of z given x, and yeah, I will disable that next time. So, we have to jointly estimate q of z given x and so on, right. How do we do that is that we estimate or rather we express all the constituent distributions that are there in our elbow using neural networks. Okay. Now represent p theta of z given x and q of z given x via neural networks is what we should do. P theta of z given x is conditional data likelihood, right? It is the likelihood of data conditioned on the latent variable. Q of z given x is the variational latent posterior density, as we know. So we have to represent both of them using neural networks. Now here is a question that I ask you. If I say that you need to estimate or rather represent a distribution using a neural network, what do I mean by that? See, even in discriminative machine learning, we represent P of y given x, which is the posterior of labels given data using a neural network. When I say that you represent a distribution using neural network, what do I mean by that? In fact, you can represent the probability distributions or density functions using neural networks in two ways. Okay, one is what I call as the deterministic representations, where the neural network will give you the samples of the distribution that it is representing. That is what a classifier would do. A classifier would represent P of y given x, correct? Given an x, it will give you samples of P of y given x, isn't it? That is what a neural network would do at the final layer. You take the generator function in a GAN, what is it giving you? It is giving you the samples of the distribution that it is representing. What is the distribution that it represents? P theta of x cap. The output of it gives you the sample of the distribution. That is one way to represent it. The other way to represent probability distribution using neural networks is that the neural network gives you the parameters of the distribution that it is representing, not the samples of the distribution. You get what I am saying? Now let us say that I have a neural network that represents this distribution q of z given x. Now this neural network takes x as an input and gives you, or rather outputs the parameters of the distribution q, not the samples of the distribution. Do you see the difference? So this is how one can represent distributions using neural networks, either using the by making that neural network output the samples of the distribution that it is representing, or by making that neural network output the parameters of the parametric distribution that it is representing. In the later case, you will have to ensure that the distribution that your neural network is representing is parameterizable. For instance, you will see that in one of the naive instantiations of VAE, we represent this distribution as Gaussian, and we take this neural network as giving the mean and the variance of that Gaussian distribution that we are that this neural network is represent. In this entire course, we will use a neural network to do both. We will use neural networks to output the sample of the distribution that it is representing, or we will use neural networks to give the parameters of the distribution that it is representing. Right? So in a variational autoencoder, the distributions q of z given x and p of z given x are represented using probabilistic neural networks. Now when I say probabilistic neural networks, I am referring to this representation where neural networks are constructed to give the samples of the distribution that it is representing. So when I say that in a VAE I am using probabilistic neural networks, I am also telling you that in this paradigm we are assuming q of z given x and p of x given z to take a particular distributional parametric distributional form, because the neural networks have to output that particular parameter of those distributions. Make sense? Okay, I think this is a good point to stop. So what we will do next is I will tell you exactly how this algorithm works. Okay, there is an issue here, is that when you are trying to represent these distributions using neural networks, this expectation, wherever we see an expectation, we would convert that into a sample average, right? But now this expectation is with respect to a distribution that is getting optimized. Now how do you optimize or rather compute an expectation in the case where the expectation is with respect to a distribution that is getting estimated along with the optimization problem is non-trivial. I will show that, and to solve that there is this nice trick, so to speak, that this VAE comes up with, which is called the reparameterization trick. Okay, so we will look at what that means. So I mean, people say that this is differentiation through sampling step and all that. We will look at those kinds of ideas the next time, and I will also tell you how to construct it and take an instantiation and show, just like I showed for GAN, right, take one instantiation and show how to backpropagate and implement it on a computer. Okay, that is what we will do the next time. Okay, thank you.